Hey everyone, welcome to This Explainer. Today, we're diving straight into an absolute mystery right at the bleeding edge of tech. We've got two fascinating concepts that, when you combine them, tell this really remarkable story about digital detective work.
Think about this. What actually happens when we reverse engineer AI and then completely flip the script and use that AI to reverse engineer hackers? That question is our roadmap today. We're going to pry open the black box of artificial intelligence to see exactly how it learns and then deputize that very same intelligence to hunt down malicious software. It's essentially a two-part detective story.
All right, let's get into Section 1, the art of reverse engineering. To kick things off, we really need to wrap our heads around something called self-supervised learning, or SSL. It's basically a machine learning technique that takes unlabeled data and adapts to new tasks. And the absolute superpower here, it learns without any explicit instructions. Literally, no one is telling the AI what it's looking at, but it just kind of decodes the data anyway. It's wild.
Moving right along to Section 2, unlocking self-supervised learning. So, what's actually happening in there? Well, this gives us our first major clue. If you track the AI from the very start of its training right up to the end, you see something almost magical. SSL inherently clusters big semantic classes together. Like, it'll totally separate animals from vehicles, naturally discovering the underlying meaning of the images on its own. It just does this.
But wait, what else is going on inside that black box? Well, over 1,000 epochs of training, the AI is actually throwing data away. Seriously. It compresses the information, aggressively stripping out all the useless noise to build these incredibly compact, efficient representations. Basically, it gets smarter by figuring out exactly what it needs to ignore.
Which brings us to Section 3, the secret of semantic clustering.
When researchers looked deep inside the algorithm, they found this fascinating tug-of-war going on. It's invariance loss versus regularization loss. Now, invariance loss just makes the AI realize that, say, a picture of a cat turned upside down is still that same cat. But the surprise, it's the regularization term that actually drives the deep understanding. It acts like a strict teacher, preventing the AI from getting lazy and forcing it to build truly meaningful categories instead of just making everything look the same.
And this understanding is deeply layered. Literally. As we dig down into the neural network, going from layer 1 all the way down to layer 10, the model's ability to cluster and separate these complex concepts just keeps getting better and better. The deeper the layer, the more profound the AI's understanding becomes. Okay, so here's where things get really interesting. What if we hand that magnifying glass over to the AI? If these models are so incredibly good at finding hidden, abstract patterns in oceans of unlabeled data, could we use them to reverse engineer highly complex hidden code for us?
Let's explore that in Section 4, AI as the detective.
Right now, the problem human defenders face is honestly crushing. The sheer volume and complexity of modern malware makes manual reverse engineering totally impractical. It's just impossible to keep up. The bad guys are moving way too fast. So to catch an automated threat, we really need an automated AI-powered detective on our side.
And that leads right into Section 5, automating malware analysis.
Here's the exact framework for integrating language models into a cybersecurity pipeline. It's essentially a brilliantly structured assembly line. First, decompiling the code, then optimizing that output, deploying the AI for pattern recognition, and finally, getting instant actionable reporting. Now, you can't just feed messy raw binary code directly to an AI and expect magic to happen. That brings us to step 2, optimization. There's this specialized framework called DGPT, and it acts almost like a translator. It simplifies the messy structure, adds helpful context comments, and renames cryptic variables. It essentially transforms total gibberish into a clean format the language model can actually read. But here's the catch, right? How do you know you didn't accidentally break the malware's underlying logic while you were cleaning it up? Well, enter MSSC, or Microsnippet Semantic Calculation. Think of it as a ruthless auditor. It meticulously verifies the execution paths and function calls just to absolutely guarantee that the optimized code operates exactly like the original. No broken logic allowed. Okay, once fed that perfectly optimized code, the AI takes over. It instantly zeroes in on indicators of compromise. We're talking malicious IP addresses, suspicious file names, covert API calls. It literally pulls hidden needles out of the digital haystack in milliseconds. To put that in perspective, a task like that could take a human analyst days to figure out. And the AI doesn't just find the threat. It actually classifies it. By mapping all these insights directly to the MITRE ATT&CK framework, it instantly categorizes the malicious code into known techniques, like credential dumping or command and control. This gives human defenders an immediate, structured playbook on exactly how to counter the attack.
Ultimately, bringing these advanced models into the mix turns the agonizing chore of manual analysis into a highly accurate, automated defense system. It's a real game changer. We've seen how AI independently learns the hidden structures of our world and how we can weaponize that very same understanding to catch digital criminals. But, it does leave us with a pretty provocative question. If AI is already this good at reverse engineering human-made malware, how long until it starts reverse engineering us? Thanks for exploring the black box with me in this explainer.